Greetings from IIT Guwahati. We are now in the module 5 of fundamentals of compressible flow, that is expansion waves and oblique shocks. So, in this module we have covered 4 lectures and the topics that were covered were Frankel-Mayer expansion waves, its governing equations, oblique shock waves, its governing equations, then also very important way of representing the oblique shock waves through theta beta m curve. Then apart from that we covered the flow past wedges and cones. Of course, the flows are supersonic flow, and also we covered supersonic flow over blunt bodies, and combining oblique shocks and expansion waves we have another theory, that is shocks expansion theory, which has been covered. Now, in this lecture we will cover some other aspects, and in particular with respect to again oblique shock waves, and those aspects are shock polar, pressure deflection diagram, and these two are nothing but another method of representing the oblique shock waves in graphical form. And as a case study to represent this pressure deflection diagram, we have framed a particular situations which we call as regular reflection of oblique shocks, and how these regular reflections can be a practical utility to demonstrate the pressure deflection diagram, and towards the end we will solve some numerical problems. So, this is all about this lecture number 5. Now, let me go to one by one, but before that we have while discussing about oblique shocks, we have first important method of graphical representation is the theta beta m curve, which is nothing but the relation between the shock wave angles and flow deflection angle for a given Mach number. Now, next approach of representing the oblique shock waves is through shock polar, and this is a method in which we represent in a form that what we call as hodograph plane. Just to give the insight that about the shock polar, this is a graphical representation of oblique shock properties of all possible flow deflection at different Mach number, but here the representations are a little bit different as compared to theta beta m curve. But here you require the knowledge about a physical plane which is nothing but the occurrence of the event, that is the oblique shock formation in a compression corner as shown is in this figure. What we have seen here, that we have a compression corner, and in this compression corner, let us say in this compression corner, that makes an angle theta b, and when the supersonic flow passes over this, it encounters an oblique shock. But here instead of representing in Mach numbers, the velocity vectors are represented. So, if you look at the flow fields before in the region 1, that is before this oblique shocks, it is purely horizontal, and purely horizontal means its x component is equal to V1, whereas there is no y component. On the other hand, in the region 2, when the flow gets deflected, then by this angle theta b, then the velocity vectors becomes now V2. So, based on this we can decompose this velocity vector as Vx2 and Vy2. So, based on this angle theta b, and what we this is what the physical in the physical plane the event was explained. But when you try to represent that same event in another plane, what we call as hodograph plane. So, the hodograph plane means you take the Cartesian coordinates, and in the x axis the velocity Vx is plotted, that means axial components in the x direction is plotted, and in the in the y directions the Vy is plotted. So, what it means is that what point A denotes the flow fields in the region 1, because it is the representative properties for the flow field in the region 1, and point B refers to the representation of the flow fields in the region 2, and this particular angle what we can say is theta b. Okay. So, one particular theta b angle, the point B is located. So, this representation we call it is that a hodograph plane. Okay. So, this is what I have explained. So, consider an oblique surface for a given Mach number or velocity and flow deflection angle in the xy plane, with x axis is the direction of the free stream velocity, and the flow fields across the shock waves is defined as the region 1 and 2. The velocity components are represented in Cartesian xy coordinates with their magnitudes and directions, and that represent behind and ahead of this oblique surface. With the magnitude of velocity vectors across the shock wave, the point A and B can be located. So, basically this point A is nothing but the entire flow fields property value, and in particular for the region 1, while point B refers to the entire flow field for the region 2, and here A and B is only the representation in the form of velocities. Now, the next step is that first thing that we located in the hodograph plane, we located the point A and we point B, we can join them as the line A and B. Now, what you do again is that you change the flow deflection angle. That means, flow deflection angle, it was originally for the point B, it was theta b. Now, we have moved to point C, which is nothing but the changing the flow deflection angle to another number theta c. So, when you do that, point C can be located. So, likewise we can join also point B to C. Similarly, you can have any infinite number of points, all possible points for the values of flow deflection angle, and at one particular point we land off a things that it will represent the theta max, means beyond this value we do not have any oblique shock solution possible. So, this point represents the theta max. So, in a sense that if when you draw all these points, we can get a curve something like we can, and what we call curve, and that particular curve we call this as a shock polar, and that shock polar is drawn for a given Mach number. And here you can see here that all other points like A, B, C, D, E, all these points can be located here. But however, here the point C is refers to the theta max, but in this location it is only for this theta c. So, means when you repeat this process for all possible flow deflection angles with respect to oblique shock solutions, till the maximum flow deflection angle is reached at a given Mach number or upstream velocity. The locus of all possible velocities behind the oblique shocks can be plotted as a shock polar, or is a graphical representation at that Mach number or upstream velocities. And in this figure, the points A, B, C are just 3 points in the shock polar. Likewise, all possible points can be located on this hodograph plane, and the locus of all these points in the hodograph plane is known as shock polar for that given Mach number. Now, let us move to do something else, that in this axis what we have plotted is Vx and Vy. Now, what you do, you can non-dimensionalize this plot. To do this non-dimensionalize, we are defining this value what we call as a characteristics Mach number, and in fact this characteristics Mach number we have covered in an earlier module. What is the significance of this characteristics Mach number is that flow fields, that is before and after the oblique shock is mostly adiabatic, and in that adiabatic situations the characteristic speed of the sound does not change. So, since the flow field is adiabatic, characteristic speed of sound is same, that is ahead and behind the shock wave. And with respect to this characteristics of speed of sound, it is possible to non-dimensionalize the velocity components by dividing it with the characteristic speed of sound. That means, your V x is now we are dividing by A star and V y is divided by A star. So, it is a non-dimensional number, and based on that we can say it becomes either m x or m y, m x and m y. And we can see that what is the significance of this, that when m star goes to infinity, when Mach number goes to infinity, m star goes to 2.45. That means, it means that very high value of Mach number can be plotted as a shock polar. That means, when the Mach number goes to infinity, the m star goes to 2.45. So, for us it is very easy or possible, for us it is possible to have very high Mach numbers to be plotted as a shock polar. So, what this particular graph is seen is that we have covered this shock polar at particular Mach number, and if you refer to one particular Mach number m 1 is 2, and we can also represent similar plots when the Mach number goes to another number m 1 is equal to 4, and likewise if you can keep on increasing the Mach number. And just for the symmetric case, we can also, since it is a symmetric, then we can also plot the similar locations in the negative y axis, that is minus V x by A star. So, these numbers can be plotted, and of course, there are two important numbers here, one is 2.45, another is 0.41. That means, these are the two limits that the shock polar existence is possible on this hodograph plane. Another important significance that we can say is that since we have plotted is through a non-dimensional number, that is characteristics Mach number. So, we can also think about drawing a sonic circle. So, a sonic circle can be also be shown in the shock polar, inside this, in which this means inside this sonic circle the velocity components will have subsonic value and it represents the strong shock solutions. Outside the sonic circle, the components of velocity will have supersonic values and it will represent a weak shock solutions. That means, on a if you look at this particular graph here, on a particular situations of or particular Mach number of m 1, and we can put and draw a sonic circles, and this sonic circle is nothing but when the speed of sound and speed of the velocity of the body are same. That means, V is equal to A, and that particular situations, instead of the in this particular plot the points will represent a sonic circle. That means, where m star becomes 1. When m star becomes 1, you can draw a circle, and this is the only 1/4 of that circle, and this particular sonic circle cuts this particular one particular curve at certain point, and based on this we can say that what are the points that remains within the circle and what are the points that remain outside the sonic circle, and what is its significance. So, this it only says that beyond these points we will have m 2 less than 1, beyond these things where m 2 will be less than m 1. So, this is what the significance of this sonic circle. And another important point, that when you draw this particular plot, the representative equations for this is nothing but the analytical equation of the shock polar, and it is represented in the form of V y, V x, and for a given Mach number m 1. Of course, they are represented in the form of m star, that m 1 is represented in the form of m 1 star. Now, let me draw some important inferences from the shock polar. So, I mentioned here already that we have already drawn a sonic circle, and this particular curve represents the all possible oblique shock solutions all possible points for an oblique shock solutions, and let us see what is the significance. The first significance is that, and for a particular flow deflection angle, that is theta, and in particular we say we refer the particular point B. So, when a line is drawn from origin O and that join from O to B, so it cuts the sonic circle, it cuts the shock polar at 2 points, that is B and D. And here you can see point D lies within the sonic circle. So, it represents a strong shock solution, and point B represents the weak shock solution because it is outside the sonic circle. So, these two possible points B and D are the oblique shock solutions for this particular theta deflection angle. So, based on this we can drop a vertical, find what is Vx by A star for the point B, and for drop a vertical on the y axis. So, we can find out Vy by A star. So, likewise we can get the velocities, and once you know the velocities we can also subsequently find other numbers. Then one of the important segment of this shock polar is that point C. So, here point C, that means if you draw a tangent. So, from the origin you draw a tangent to this shock polar, then it will cut at point C. So, that represents the maximum flow deflection angle, that is nothing but theta max. And if you can see here, at this particular point there is only one solution, and you will find that it will be cutting somewhere which is close to the sonic circle. So, it represents the maximum flow deflection angle. Another important significance is that point E and A. So, point E and A on a shock polar will represent two possible extreme situations. So, the point E refers to the normal shock, and because it is within the sonic circle and it lies in the abscissa, and whereas point A refers to a Mach wave situation, or it is a Mach line, and it also lies on the abscissa. And if you refer these things with respect to oblique shock, that means at a normal shock situation we can say this point refers to point E, that is 90 degree, shock wave angle is 90 degree, and point A refers to this particular region, and it lies where we can say it is a Mach line, and Mach line for that given Mach number. For example, for Mach number of 2, so point A is located on this axis, where for which the shock wave angle is only 30 degree. Okay. And another important point that we are supposed to know is that always if once you have this point E and A, this point lies on the oblique theta beta m curve, that is on the abscissa on the y axis, and where the shock wave angle is represented. Now, for any other particular situation, if you want to find the shock wave angle, then what you do is that we can draw a, for example, if you want to at point B, if you want to find what is the shock wave angle for a given theta, and Mach number, if you want to find the shock wave angle, then you can join the point A and B and extend, and side by side from the origin one can draw a line OH which is normal to this curve AB. So, we have this line OHA angle as 90 degree, and OHA angle is 90 degree. Another angle we can have is AOH, that is nothing but the beta, and it represents the shock wave angle. So, this is all about the shock polar. Now, you are going to represent another graphical method which is known as pressure deflection diagram. So, pressure deflection diagram is nothing but a representation where the static pressure values are plotted against the flow deflection angle for a given Mach number. This is how it is plotted. Now, here in the x axis it is nothing but your flow deflection angle, in the y axis it is your static pressure value for an oblique shocks. And here we represent two possible situations and of oblique shocks, what we call as a left running wave, other is right running waves. So, left running wave means that whatever oblique shocks we have represented, most of them are left running waves, and here where the flow is turning towards itself. Another way of representing same phenomena is that if you can orient these oblique shocks and where the flow is deflected, and here it is a negative theta directions. So, we will come back to this point later, but for the time being let us see that the method of graphical representation is the locus of all possible static pressures behind the oblique shock is a function of flow deflection angle at a given Mach number, and such a representation is known as a pressure deflection diagram. And this oblique shock of two different orientations are represented through a pressure deflection diagram. One of the important thing that one has to remember that the oblique shock deflects the flow towards the wave, and this possible situation can be possible for a left running oblique shock, or also it is possible for a right running oblique shock. Now, when you say it is a left running wave, it means that when you stand at a point on a left running wave and look downstream, it appears that wave run towards the left and the flow deflection angle is upward and it is considered as positive. So, that is flow deflection angle when it is positive, that means the flow is turned upward in the upward direction. So, it is theta 2 here in this case is a positive. Now, similar picture also we can say in a right running wave, and when you look downstream the wave appears to turns to the right and the flow deflection is downward. So, it is considered as negative. For a given Mach number, one can think of a left running wave oriented in this fashion. For same Mach number, we can also think of a right running wave oblique shock, and there the flow deflection angle will be considered as a negative. So, in this case what we are saying that as if the wave is moving. So, it is a moving frame of reference. So, based on this concept of left running and wave and right running waves, the point 2 for a left running wave is can be located. That means, for when you for a given Mach number, first you locate the point 1. So, point 1 can be represented with theta as 0, which is for this region 1, and for this region 1 static pressure is known. So, we can denote this point 1. Now, when you have moved to point 2, so that means we have moved by angle some angle theta 2. So, point 2 can be located. For that for this point we know the Mach number, we know the beta value from theta beta m curve. So, we can locate this point B side by side. For same flow deflection, if it is a right running wave, we can drop we can have another value theta 2 dash in a negative directions, that is negative flow deflection angle. So, point 2 dash can also be located. Likewise, if we can keep on changing this theta value, we can reach a location what we call as a theta max for that given Mach number. So, one particular shock what we can say pressure deflection diagram can be plotted, that is for Mach number m1, and likewise for this particular point it represents the maximum pressure that is possible from this particular situation. Now, when there is no deflection angle, the static pressure ahead of the shock is P 1 and the static pressure behind the shock wave is P 2, which is denoted as P 2 for a left running wave and denoted as the region 1 and 2, and similar conditions at negative flow deflection angle can be drawn for a right running wave and it is denoted as the region 1 and 2 dash. So, for all possible values of flow deflection angles of oblique shock solutions, the locus of all possible pressures at a given upstream Mach number is represented by a pressure deflection diagram. So, we have demonstrated two things, one is shock polar, other is the pressure deflection diagram as a representation of oblique shock in graphical form. Now, let us see a practical situation in which we feel that importance of at least one particular diagram, that is pressure deflection diagram, is realized. One such situation we can say is a regular reflection of oblique shocks. In a moving shock situations, when at least when the shock wave is moving in a duct or some kind of enclosed chamber, then such type of things is a routine phenomena. And one such phenomena what we can see is that we have a situation that there is a compression corner which is at a point A, and this compression corner is located through an angle theta, and the supersonic flow encounters it, and because of this there is an incident shock, and this incident oblique shock is oriented by an angle beta 1, and what happens is that this incident shock, when it impinges on a upper solid wall. So, there is another solid wall, solid surface, and this incident shock impinges on this solid wall at point B. So, obviously, it has to reflect. Now, when it has to reflect, the reflected shock orientation should be such that the flow streamlines in the region 3 should be parallel to this upper solid wall. Now, if you look at the streamline point of view, you can say that streamline in the region 1 is parallel to this surface, that is horizontal, that is means horizontal means it is parallel to the bottom surface and the parallel to the top wall. Now, after the oblique shock, the streamline gets deflected. Why it is deflected? Because of this, it sees a flow turning angle for this compression corner. So, it is deflected, and this through this deflection process and with this shock wave angle, the flow is deflected by an angle theta. Now, when it is reflected, had there been no reflected shock, the streamline would have extended with this deflected line, that is dot dashed line. But what happens is that due to this reflected shock, the streamline must be parallel to the solid wall, which is solid upper wall. Since it has to be parallel to this upper wall, the flow the streamline must deflected by downward, means with same magnitude of theta. And because of this, since the conditions 2 and 3 are different, the oblique shock orientation would be a different beta value. So, we call this as a beta 2. So, in summary, what happens? The incident oblique shock impinges on an upper solid wall at point B, it comes as a reflected shock, and because of this reflected shock, the 3 different regions have been formed, region 1, region 2 and region 3, and region 1 is the upstream conditions or free stream flow, region 2 is the properties after this oblique shock or after the incident shock, region 3 is the properties after the reflected shock. And we will see that the angle that makes phi is nothing but you can find this angle phi, which is nothing but beta 2 minus theta. Okay. So, and when these particular situations are plotted, we must remember that this condition is maintained, means that this theta angle is always less than theta max for M2 and theta max for M1. So, on a theta beta M curve, one can find the maximum flow deflection and angle theta max for a Mach number M1 and M2, and this theta is less than that. So, that means this ensures that the incident shock will give you a attached shock situation. So, this is what I have exactly mentioned, that in the region 2 the streamlines are now inclined in the same deflection angle. All the flow properties in the regions depends on the upstream Mach number parameters. In order to remain for the flow to remain parallel to the upper wall, streamlines in the region 2 must be deflected downward through same angle. So, there must be a second oblique shock of sufficient strength that must originate from the point B, so as to turn the flow with adequate angle, and this second shock is known as reflected shock. We are now going to realize the importance of the theta beta M curve, and in particular because all the possible solutions are obtained from this theta beta M curve, side by side we can see that this particular situation represent, that means here the incident shock A B resembles, it is a left running oblique shock, and the reflected shock is a right running oblique shock, and these two waves and the flow fields across these two shocks are completely different, except the common phenomena that flow deflection angle theta remains same. So, in a sense that we can simply realize the importance of pressure deflection diagram here. So, to locate these points 1 and 2 and 3, let us see this particular figure, that is P theta curve, and in the P theta curve, first thing that we must know that we have to find this P theta curve for the Mach number M1 first. So, because the M1 is the source or the upstream parameters in which the incident shock is oriented. For this Mach number and for this flow deflection angle, we can now locate the point 2. So, point 1 is located with no deflection angle, that is theta 0, and point 2 is located for this particular angle theta and Mach number M1. So, likewise, if you keep on changing this theta for this M1, one can draw this particular curve, and this curve is drawn for Mach number M1. So, it is a pressure deflection diagram for the Mach number M1. Now, for this reflected shock wave, now we are already in the region 2, and for this region to draw this shock polar, again you have to drop a vertical, and here the shock polar should start from the point 2 for the Mach number M2. So, here it starts with some static pressure value, which is P2, and but here if you see that it is a reflected shock. So, it is a right running wave, that means, and again the point 3 will be located on this axis, because the flow field is again deflected by same angle theta. That means, initially we went theta in this direction, again we came back in theta for same value of theta. So, theta remains same. So, the point 3 can be located at this point. So, in a sense that for likewise another P theta diagram can be drawn for Mach number M2. And if you keep on extending these situations, a multiple number of pressure deflection diagrams can be drawn for different Mach numbers, across which the possible values of static pressures can be plotted. So, this is how the importance of a pressure deflection diagram is realized for a regular reflection of oblique shocks. And most important information that is realized here is that we can cater the left running wave as well as right running wave in this p theta diagram. And here the incident shock is a left running wave, because of which the condition in the region 2 is denoted with positive flow deflection angle. So, point 2 and once you know this point 2, we can draw another p theta diagram corresponding to the Mach number m 2. For the region 2, the vortex is at point 2. So, because the free stream for this Mach number is m 2 with same upward flow deflection angle. So, but the reflected shock is a right running wave. So, the flow deflection angle will continue in a negative directions, and till its value is again becomes 0, that is trim lines becomes parallel to this upper wall. Okay. So, with this we have covered these two important diagrams, that is shock polar and pressure deflection diagram as a graphical representation of oblique shocks, in addition to earlier portions that is covered, that is called theta beta m curve. Now, we are going to solve a numerical problem based on a regular reflection of supersonic flow in a compression corner. So, you have to consider the previous example, which is nothing but a regular reflection of supersonic flow at Mach 2 from a solid boundary. The upstream static pressure and temperatures are known to us, and in the first compression corner the flow is deflected by an angle 16 degree, because of which an oblique shock is generated and it propagates into the flow, and finally it becomes incident on a horizontal wall. So, you have to calculate the angle made by the reflected shock with respect to wall, Mach number, pressure, temperature and behind the reflected shock. To solve the particular problem, we have to first draw the physical problem, and we have to represent what do you mean by a regular reflections of supersonic flow, and there is also a solid boundary which is the top surface. So, if you recall our previous discussion, if I draw this particular diagram, what you can say, we have a compression corner. So, this particular things represent the fact that in the compression corner we will have an oblique shock, and we call this as an incident shock. So, your upstream conditions are M1 and P1 properties are T1, P1 and T1. So, the angle made by this compression corner is theta. So, I will put it as a theta, and for this shock wave angle will be beta 1, and this incident shock now interacts with a solid boundary. So, you can have another solid boundary which is located in this fashion. So, that means this incident shock goes and impinges. So, when it impinges at point B, and because of this reason there will be a reflected shock. And you can see here, if you look at with respect to streamlines, so in the region 2, so you have region 1, region 2 and region 3. So, in the region 2, the streamlines is deflected by an angle theta. So, we can say is M2, and finally, had this flow been deflected in this fashion, it would have gone in this way, but however, in the region 3 the solid wall is horizontal. So, the flow also must deflect by same angle, that is theta, and the shock wave angle will be now beta 2. One important thing is that theta remains same in both the cases for the both incident shock and reflected shock. So, the question that was asked to us is that we have to find the angle made by the reflected shock with respect to solid wall, that is beta with respect to solid wall. So, this beta 2 is with respect to this dashed line and we have to find with respect to solid wall. So, we have to can say had this been parallel to this. So, we would have, so it can represent this as a phi. Okay. So, we have to calculate this phi and P 3, T 3, M 3. So, these are the question mark we need to calculate. So, we will solve the problem step by step. So, first step is, so you have to go from the for the incident shock. So, let us solve the problem first with incident shock, and we have to recall the theta, beta, m curve. So, what is known condition given to us? M 1 is 2.8 and theta is 16 degree. Okay. So, you have to so somewhere on this theta beta m curve 16 degree will be somewhere in this line and it will cut this Mach 2.8 flow. So, that means close to curve C, and roughly if you can drop a vertical in the beta axis, this we can locate this particular point, and this beta 1 in this case would be approximately 35 degree. So, once you have known beta, so you can find out m n 1. So, m n 1 is m 1 sin beta 1. So, m 1 is 2.8, beta 1 is 35. So, you can find out m n 1, this value is 1.6. So, once you have this m n 1, we can refer normal shock table. So, normal shock table for m 1 is 2.8, sorry, m n 1 is 1.6, somewhere in this number. So, we can note down this value as P 2 by P 1 2.82, T 2 by T 1 1.388, and we can have m n 2 0.6684. So, once we have m n 1, we have m n 2. So, we can all now calculate m 2 is equal to m n 2 divided by sin beta minus theta. Beta 1, here beta 1 is 35, m n 2 is this, theta is 16 degree. So, m 2 can be calculated as 2.05. Okay. So, once you have this m 2 as 2.05, then you have to repeat this calculation for region 3. So, for again we have to revisit this m 2 2.05, theta for the region 3 again is 16 degree. So, for same 16 degree, if you go to close to this, that means if you extend this line and finally drop a vertical in the beta axis. So, this particular point will give you beta 2 value. So, beta 2 can now be close to 45 degree. So, once you know the beta 2, we can say m n 2. M n 2 will be m 2 sin beta 2. So, m 2 is 2.05, beta 2 is 45. So, Mn2 will be 1.46. Now, for this Mn2 1.46, we can again refer this normal shock table and note down the value. So, we will note down the values that P3 by P2 would be 2.32, that this refers to Mn2 is equal to 1.46. P3 by P2, T3 by T2 is 1.294, then Mn3 will be 0.7157. Then we can calculate M3 as Mn3 sin beta 2 minus theta. Okay. So, Mn3 is noted here 0.7157 sin, and beta 2 is already, it is 45 degree and theta is 16 degree. So, this number would be 1.45. So, we can say the Mach number after reflected shock that is region 3, we have M3 as 1.45. So, if you see here, after your initial Mach number was 2.8 and in the reflected shock Mach number will be 1.45. Then we can now calculate the values. P3 is equal to P3 by P2 into P2 by P1 into P1. T3 is equal to T3 by T2 into T2 by T1 into T1. So, these conditions are known, that is pressure is 1 bar, temperature is 298 Kelvin, 290 Kelvin, P2 by P1 and T2 by T1 are known with respect to M2, T3 by T2 and P3 by P2 are known with respect to Mach number M3. Okay. So, once you know all these things, these ratios are known to us. So, when you put these numbers, we can say P3 will be 6.5 bar and T3 would be 521 Kelvin. Another parameter that remains, that angle made by the reflected shock with respect to wall, that phi. As I mentioned, from the geometry of this figure, the angle can be calculated as phi, which is nothing but beta 2 minus theta. So, beta 2 already we calculated as 45 degree, theta is given to us which is 16 degree. So, phi would be 29 degree. So, interesting point is that for the incident shock, the beta 1 angle was 35 degree with respect to horizontal and reflected shock makes an angle 29 degree. So, obviously, these two are not equal. So, this means phi is not equal to beta 1. So, this conclusion what we can draw is that the shock wave is not specularly reflected. Because it is not specularly reflected, the conditions 3 are different from the condition 1. at this angle been equal. So, M3 condition would have again same as M1. Okay. With this I conclude for this talk today, and thank you for your attention.